Steve, it's and hi everyone. It's great to be here again for a new course. Probably I should tell a couple things about my background. Actually, my university background is pure mathematics. I majored in mathematics and computer science, but then finishing my PhD in mathematics, I got interested in radio communications and radio signal processing, and that's what led me to a career in industry doing satellite navigation with mainly with the European Galileo system, which is the equivalent to GPS. But nowadays I'm doing contracting full time in spacecraft communications, and part of that is using GNU Radio. So I'm glad that with the company I'm working with, we launched a satellite the previous week, and the ground station, so that means all the equipment on ground, which is communicating with the satellite, runs fully with GNU Radio. So there you have a real world application of GNU Radio being used in industry for a product which is in production.
Great.
Okay, the first thing I wanted to know is if everyone has been able to install GNU Radio in their computers, or if there's someone who has found an issue. Often we have had some trouble with Apple ARM computers. Those tend to be the most problematic. So if anyone has any difficulties, please let me know either now or in chat. I'm here to help, and I don't have an Apple machine here, but I can ping people who have one, and we can test and try to make a GNU Radio work in everyone's machines.
Did anyone not manage to install GNU Radio? All right, everybody managed to install it.
Yeah,
that's
that's a success. I remember, I think it was 2021 when the M1 laptops came out. That was madness because they came out weeks before the summer, and no one had yet had a try at using GNU Radio or other open source applications on those machines, and support was sketchy. But now it seems things are much better. So without much further ado, I have a few slides I can share as an introduction to what is GNU Radio, how it's used, etc., etc. Let me arrange my screen properly for this. Okay. There we go. I think I'm already sharing screen. Yeah, I can see it, in fact, on the webcam. So GNU Radio is an open source framework or application, if you wish, to develop, to program DSP, that's digital signal processing, mainly for radio applications. That means radio communications, radar, radio astronomy, anything involving radio. You could also use it for audio processing. There have been some people who have used it for music production, such as guitar distortion effects or similar stuff. But the main focus of GNU Radio is radio signal processing. It is also an open source project and a wide community. It's the wider community involved with signal processing and radio. So I guess the most fundamental part of GNU Radio is actually the project, the people around it. It's a bunch of very interesting people coming from industry, from academia, or even hobbyists who do really great job. GNU Radio has mainly three different pieces or aspects to it. One of them is GNU Radio Companion. It's a graphical user interface application. Maybe you've already started up GNU Radio Companion in your computer, probably after installing GNU Radio. And there you can implement systems by dragging and dropping blocks onto a canvas and connecting them together. This is similar to Simulink, if you have used MATLAB or Simulink. So the idea is you have blocks representing different processing functions, and the processing functions can be as simple as sum two real numbers or two complex numbers, or they can be as complex as this is a full digital television transmitter. So on the input, we put some video data, and on the output, we get the digital video waveform ready to be transmitted by satellite or whatever. And so we connect these blocks and make what is called a flow graph. So the flow graph is the collection of blocks together with their connections. To make this useful, GNU Radio has a library of blocks, which can be accessed through GNU Radio Companion, as I have explained, but they can also be accessed from C++ and Python. I guess most of you are familiar with Python. So actually, the flow graphs you draw in GNU Radio Companion have behind them a Python script. GNU Radio will generate for you a Python script, which instantiates the blocks and connects them using Python. And if you need to do more complex applications, then you can do it in Python, or you can embed a Python flow graph inside a larger Python application. And you can do the same with C++. And finally, there is a runtime. The runtime, or the engine, is the part that decides which blocks need to be run at each time and how to move the data between these blocks. So this is quite useful because this is really low-level stuff. And also computers nowadays tend to have many CPUs, especially large server machines. And oftentimes it makes sense to run stuff in parallel in all the CPUs. So what happens is that GNU Radio will run each of your blocks in a different thread and use the operating system to decide what needs to be run, what has available data as input, what can produce output, what can be moved to the next block, etc. And this really saves us from the effort of rewriting these low-level data movement and management stuff every time we want to write a new radio application. In the GNU Radio ecosystem, we have something which is called an out-of-tree module. It is called out-of-tree because it's outside of the source code tree for GNU Radio, which the GNU Radio project maintains and develops. And these out-of-tree modules are like extensions or plugins. So they implement new blocks, which can be maintained by anyone. I maintain a few out-of-tree modules, and there are many other people maintaining their own out-of-tree modules for different applications, which are usually too specific that they don't really fit into the GNU Radio in-tree library. And there are also full applications which use GNU Radio to do the digital signal processing. An example of that is gqrx, and we will see gqrx in a moment. So you might have any application which needs to do radio signal processing, and it might not be evident that it's using GNU Radio behind the scenes as the backend to process data. So that's the case with gqrx. gqrx is a graphical user interface to receive radio using an SDR. So I have here my RTLSDR. We will be using that later today with gqrx and GNU Radio, and you'll be able to see that gqrx doesn't really look like it's using GNU Radio. But if you go to the C++ source code of gqrx, you will see that it's using GNU Radio for all the signal processing. Okay, so this is a very simple example of a flow graph in GNU Radio Companion. This is how the flow graphs you draw in there look like. And here we have two blocks. They are signal sources, so they are generating a signal. It's a cosine. So everyone knows your sinusoid functions. They are the most simple signals you can have because in the frequency spectrum, they are just a single tone. And here we are generating two cosines of 1 kilohertz and 1.5 kilohertz. So all of these are parameters. So we can double click on the block and the window will pop up to change parameters. Next, we add these two cosines. So we end up with a signal which is composed of two tones at two different frequencies. We have this throttle block. So what the throttle block does is to limit the rate at which samples are flowing through it. If this throttle block were not present, then samples would flow at as fast as your computer is able to keep up. So basically, you would have something that is producing samples very, very fast, and you would have 100% CPU usage on your machine. And that's probably bad because it generates a lot of heat if you're using a laptop, etc. So when we have flow graphs such as this one, which doesn't involve any hardware, there isn't an SDR receiver here, there isn't a sound card. We will see examples of flow graphs with hardware later on. There is nothing other than this throttle block to set the rate at which data is generated or moved through. So unless we want to run as fast as possible, we need a throttle block to limit the rate at which data is flowing. And in this case, we are throttling at the sample rate. That means this is a real-time simulation. So it is simulating at 32,000 samples per second, and this is limiting the amount of data at 32,000 samples per second. So things will evolve or will be generated as if they were being played in real time, if that makes sense. And then what we do with the output of the throttle block is we have this TCP sink. So a sink is a block which has an input but has no outputs. And in this case, TCP is a network protocol. So this is a server for TCP. And what this does is it starts up a TCP server, and you could have an external application connecting to the TCP server and receiving the samples which have been generated here. So this is a simple example of how just dragging and dropping a few blocks, we can generate a few simple signals and send them using the TCP network protocol to a different application. Any questions so far? Okay. This is how the same flow graph looks like in Python. I don't want to get into much detail with this, but I just wanted to show this so that you can see that it's not so complicated. So the flow graph is represented in Python as a Python class. And then in the init method, which creates the class, you have this top block, which creates the flow graph itself. And then you have all these function calls to instantiate each of the blocks. And you can see that it's fairly natural to relate these to the previous diagram. So we had a TCP sink, and this is the data type. By the way, complex data type. I haven't spoken yet about data types, but I will do. This is the IP address. Probably if I scroll back, no, that's a default option. So probably if we double click here, we will see more options which are hidden in the diagram. But we have the option for the IP address and port. There's the throttle block here is using sample rate as the sample rate. Sample rate 32,000. That's a variable. It's a regular Python variable. Nothing funny here. There is at VCC. CC stands for complex input, complex input, complex output. That's the reason you have two Cs. And the one is the vector size, and you could omit that. And then you have your signal sources. So for example, here, cosine wave, 1.5 kilohertz, 1 kilohertz. And finally, when you have instantiated all the blocks, you connect them together. And connecting is simple. You call this connect method. And what you do is block output number 0 goes to block input number 0. So that's this first connection. Then this is signal source 1. So this is the second one with the 1.5 kilohertz. output number 0 goes to input number 1 on the add block. So that's the second connection. And you could keep going and write fairly complicated blocks, fairly complicated flow graphs. And in fact, one advantage of using Python for this is that you can do this programmatically. So imagine that the flow graph we want to do needs to have, I don't know, 128 different blocks. For what particular reason? For example, channelization comes to mind. In radio telescopes, it's quite common to use a polyphase filter bank to channelize your signal, and then you end up with multiple channels that you need to process separately. So you might want to do the same thing in those 128 or 1024 or however many channels, and you would need to instantiate a block for each of the channels. And well, doing that by hand on the graphical user interface is very cumbersome. You could maybe do 64, but doing 1024 channels is a bit of a stretch, really. So what you can do is to use Python, and then you can have a for loop. And with a for loop, you can create not one, not two, but as many processing blocks you need, and also do the connections with a for loop. So that's the advantage of using Python here. Whenever you have something which is regular or that you can program in an algorithm, you can do things in Python and save you some manual work. And also another advantage is here we have the main method. So this, or the main function actually, this is the function that gets called when you run the Python script. And here the only thing happening is we are starting the flow graph and waiting for it to finish. And in this case, the flow graph never finishes because it's a simulation, or because we have two signal sources which do not really have an end. The kind of flow graphs which do have an end are those where you have a recording you have done and you want to process that. So you start reading the file, and at the end of the file, then there are no more samples to finish to process. So the flow graph finishes. But many, the most common type of flow graphs in GNU Radio run forever until you stop them, because either they are a simulation with something which is generated continuously, or you have an SDR receiver, and your SDR receiver is running continuously and sampling the radio frequency spectrum and sending that to your computer. So in case you have a more complicated scenario, maybe you have to do some stuff here in the main function. For example, observing with a radio telescope comes to mind. Usually in an observation with a radio telescope, you observe different sources, you observe some calibration sources, you observe your target of interest. So what you do is you move your telescope to the first calibrator, then you record data for a while, you run some calibration functions, then you apply the calibration, then you move to the science target, and then you record data for a while, potentially in a different manner, and you process data. So you could have a Python script, and in fact, we have some working with the Allen Telescope Array that does all that. It might use the Python API of the telescope to move the telescope, to run calibration, to collect data, and then call some GNU Radio functions to process the data either in real time or the data which has been recorded beforehand. And then you can move on to the science target, and you might have a list of targets and right ascensions and declinations, because this is Python. So it's very easy to handle that with AstroPy, and you could have your flow graph run through all of those with a for loop using Python. So that really gives you a lot of flexibility. And if writing all of these seems a bit daunting at first, what you can do is to generate your Python code in GNU Radio Companion, and then you can either import that in Python, because it's Python file, so you can import, or you can copy and paste and modify as you need. So you can use the automatically generated code such as this as a starting point to customize what you need. Okay, some motivation, because in these tutorial sessions, we will be starting with really simple things. And I think even if simple, they are fun and interesting. But I also want to give you an outlook perspective about how GNU Radio can be useful beyond what we will do in these sessions. So in which applications, or what are examples of applications which have to do with either SETI or radio astronomy that I think GNU Radio can be useful for? The first is as a full backend for small radio telescopes. And full backend means do all of your telescope signal processing needs. And by small radio telescopes, I mean educational radio telescopes, which often do not collect a lot of bandwidth or do not have a lot of antennas in the case of an interferometer. Why have I decided to include here small radio telescopes? Well, the reason is that, to be fair, GNU Radio is a very broad topic application. It's intended to do many different tasks and to do them well, but not very, very well. So while it excels on the amount of different things you can do satellite communications, you can do radio astronomy, you can do digital TV, you can do, I don't know, radar. But it's not going to be as efficient in each of those tasks as a tool which is written specifically for just one single purpose. And that's very clear in radio astronomy, where people are often putting computing power to the limit and trying to sample more bandwidth or trying to use more antennas. So in that case, it can be a bit difficult to use GNU Radio with the required performance. In fact, we have a real world experience with that. In the Allen Telescope Array, we tried to develop a real-time correlator for the antennas. And that was working, but it was working only in real time with, I don't remember, maybe 8, 10 antennas or something like that. The Allen Telescope Array currently has 20 antennas in service, and a few more of them are operational and will be brought into usage in hopefully this year, if not next one. And what it uses for its correlator is something which is called hash pipe. So hash pipe is a processing pipeline written having radio astronomy specifically in mind, and it beats GNU Radio performance by quite a bit. So yeah, I would be lying if I tell you you can go to any major telescope in the world, deploy GNU Radio there, and it will work beautifully. That's not the case, but even so, it's a useful application. There are people who have small educational telescopes and run everything in GNU Radio because it's much easier to do all the processing you need on your own rather than use hash pipe or anything else, which is definitely more complex. What else? RFI analysis and simulation. So RFI stands for radio frequency interference. That's the main enemy of radio astronomy and also SETI. We want to observe signals which are often very weak, and we don't want strong signals which are human-made and are transmitted by everything which is electronic near the telescope and also satellites, because there are many satellites in orbit currently. So it is a huge topic, how we can detect RFI to avoid it or to mitigate it, how we can coexist with other services and maybe have the other service shut down when radio astronomy observations are done, or maybe agree on what slices of spectrum each service will use. So RFI analysis is a huge topic these days in radio astronomy. And GNU Radio is very well suited for it because it has such a rich environment of applications that if you want to simulate RFI from some particular system, I want to simulate RFI coming from 5G base stations, you can probably have a GNU Radio application which is generating actual 5G signals like valid 5G base station signals, you could connect your cell phone to that. And what would be best than something which is exactly like the actual waveform you want to study than that. So that's a reason. What else? A similar topic: simulation of techno signatures and other signals of interest. So in SETI, we try to detect signals being transmitted from advanced extraterrestrial technologies. And currently, the most common type of signal which we try to detect is what is called a narrowband signal, which will typically have a Doppler drift because everything is moving in space. So the Earth is rotating both around itself and also around the sun. Potentially, the transmitter for this technosignature would be on a planet or in orbit, so it will also have a Doppler effect due to that. So that's the main thing we try to detect. But there are other different types of signals, such as wideband signals. And if we look at our current communication protocols, most of them are wideband. Most of them do not have any narrowband carriers, which would specifically show up in any of these traditional SETI searches. So there are other more advanced signal detection algorithms which are currently being studied for SETI, and GNU Radio can be a good platform to simulate your technosignature waveforms and to prototype your detection algorithms. So that brings me to the next topic, which is as a prototyping platform for any kind of signal processing algorithm, it's great. As you saw, you can generate some data easily. You can run that through your processing blocks, and it's quite efficient doing so, even though not as efficient as HashPipe or specific application, but it's quite efficient. And finally, what we are actually doing in these sessions, teaching signal processing. I think it's much more meaningful to study signal processing using examples and using some flow graphs or some applications that you can interact with, and you can visualize the signals and change some parameters and see the effects, rather than going to the textbook and studying some formulas, doing some calculations on paper and imagine how things would work. Of course, if you want to get very far in signal processing, at some point you need the textbook formulas to really understand what is going on. But even so, the intuitive understanding of seeing things actually working in either in the real world or in a simulated environment with GNU Radio is very valuable. Okay, so enough talk with that. What I want to do now is, to present a few links. This is probably not needed because everyone has GNU Radio installed, but the easiest way to install GNU Radio is Radio Conda. This is a one-click installer for Windows, Linux, and macOS that will install you a Conda environment, which comes with GNU Radio and a bunch of applications based on GNU Radio or having to do with GNU Radio, such as the drivers you will need for the RTLSDRs you have. Second link, and I'm going to paste this in the Slack channel, is the GitHub repository for this session. So I will be uploading all of the materials, GNU Radio flow graphs, perhaps some recordings and similar stuff to this repository, and you can download in advance. I will try to upload ahead of each session the flow graphs I will use, and oftentimes I do them again from scratch just because it's easier to follow. But if you don't want to follow along in your machine, you can download those and you have a perfectly running flow graph. You can click play and run. And you also have the previous year's material. So we have done these sessions in 2022 and 2021. I will probably repeat some of the stuff from previous years because it's good and it's also important. But probably there will also be new things this year because I also like to do a few new things every year. Okay, any questions at this point? Great. So the next thing is I want to demonstrate how to use the RTLSDR stick. You probably have a stick like this. Maybe it's not in a metal case, but it should have a USB connector. It should have an antenna connector. This is called an SMA connector. Maybe the one you have has a different connector, but it doesn't matter. Any kind of simple antenna will do. I have this one. And what I'm going to do is to plug this into a USB cable, which goes to my computer. And I will leave this here. So I'm going to run gqrx. gqrx is, I'm not sure if it comes with Radio Conda, by the way. Maybe let's check. If not, you can, I think it doesn't, but if not, you can install it. It runs on Linux, Windows, and Mac OS. And if you don't want to use gqrx, or you find any problems with gqrx on your machine, there are also many similar applications. So I can share a list of alternative applications to gqrx. I want to get started with gqrx instead of GNU Radio, just because it's easier to use a ready-made application to use the RTLSDR for the first time. And also, if you haven't tested if your RTLSDR runs on your machine, it's probably the best way to do it. So yeah, this is giving me an error because the previous SDR I was using, which is not the RTLSDR, is no longer plugged in. So it tells me to select a new device. And depending on the kind of drivers you have in your system, you will get a different list. As you can see, there is something for a complex sampled IQ file. This is a recording, so this is not hardware. This is a pre-recorded file that you could have in your computer. Then I have a bunch of network receivers. So since these are supposed to be network receivers, they show up just because I have the drivers installed. I do not have any of these in my network, but my computer doesn't know, so it's offering those as options. And then I have two different options for the RTL. Anything which looks like RTL blah 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 is the RTLSDR we want to use. And the two options are quite similar. I'm not sure if they use slightly different drivers, because there are different driver stacks you can use with the RTLSDR. So I'm just going to pick the first of them. And it fills for me the device string, which specifies the driver and a few other options, which are different for each SDR you might need. The next thing we need to select is the input rate, or input sample rate. That means how many samples per second the SDR is generating. So briefly speaking, what an SDR does is to sample the radio frequency spectrum, or a slice of bandwidth in the radio frequency spectrum, which it obtains by doing some filtering and frequency conversion. And it generates digital samples, discrete samples. It uses discrete time sampling. And the amount of samples per second that it generates is what we set here on the input rate. So why is this important? This is important because depending on the bandwidth we want to be able to represent or process or receive, we need one sample rate or another. More specifically, there is something which is called Nyquist theorem, and it says that for complex sampling, and this is quite important, most of the SDRs that are common use complex sampling. That means they deliver complex numbers with a real part and an imaginary part into the computer. We will see in more detail how this works, but it's just a mathematical trick which makes some signal processing tasks much easier than if we were to use real numbers. which might be the more intuitive way of representing radio frequency information, because in the end, the data will represent is the voltage at the antenna, not in volts units, but in some arbitrary units, but it's the voltage, radio frequency voltage coming into the antenna connector on the SDR. So coming back to Nyquist theorem says that the bandwidth I can represent with complex sampling is equal to the sample rate. So in this case, it's 1.8 million samples per second. That means I can represent 1.8 million hertz or 1.8 megahertz. So any kind of signal that fits into 1.8 megahertz, I can represent or receive with this setting. Any signal which is too wide, I will only be able to look at a smaller 1.8 megahertz piece of that. I'm going to change this because the most usual or most common sample rate is 2.4 megasamples per second to use with the RTLSDR. You can even push it to 3.2 megasamples per second often, but it might get too hot, the SDR itself. It might even crash depending on, I don't know, temperature or your USB drivers or something. 2.4 is a good and reliable value to use. And it will be probably sufficient for all we will do. Bandwidth, some of the SDRs have some filters where you can select bandwidths. I think this option doesn't do anything with the RTLSDR. So we set it to 0. And also decimation, we set it to none. Here it can be a bit confusing because most of the applications that are out there are written in mind with supporting many different SDR devices. So there are not only the RTLSDR, there are many other different devices with different capabilities and different settings you can change. So they try to offer all those settings to the user, and in some cases those settings do not make sense for a particular SDR. In this case, bandwidth, I think it doesn't do any effect with the RTLSDR. And the audio output, we select the default settings. So okay, hopefully if you have this on your computer or if you try afterwards, you will have something similar. I can start receiving by pressing this play button, which says start DSP. And then I get something here, which is the spectrum. So this represents frequency. Here is the frequency in megahertz, and power. So power versus frequency. The power is in dBs or decibels with an arbitrary scale. So if we wanted to relate this power to milliwatts or Janskis or anything at the antenna connector, we will need to do some calibration. Input controls, in here, the most important thing is the gain, which we will see in a moment how to use the gain properly. And the antenna connector, in the case of the RTLSDR, you only have one antenna, so this list only offers me a single option. So what can we do with this to actually test that it is working properly and that you can receive the signals, nothing is broken, etc. Because at the moment, what we see here is what is called the noise floor. So this is just random noise coming both from the device itself and also radio frequency noise. Everything generates radio frequency noise just because of its temperature, and also electronic devices generate all sorts of radio frequency noise. And there are a few radio frequency interference things here. So the easiest thing is to tune to the broadcast FM band. That is around 90 or 100 megahertz. So I'm going to tune to, actually, I need to click somewhere. So if you click somewhere here, you will get this red line, and that means you are tuned to this frequency. So think of your radio receiver on your car or something. And then I'm going to do 98.8, and I know this is a local radio station. So this is the radio station. You can see it here in yellow, and also as a bump in the spectrum. And there are some other weaker radio stations. So mostly everywhere in the world, and in Berkeley for sure, if you tune to this frequency band somewhere between 90 and 100 megahertz, you will see FM radio stations. The thing I want to show is how to use the gain control. So this is the gain control, and at the moment it's set at a minimum. So the minimum value is 0 dBs, and I can see this is all the way to the left. If I increase the gain, we can see that the signals come stronger, but we can also see that some nasty stuff here, some interference appears on the spectrum. Maybe that's just because of the previous gain was too weak to show us everything. In fact, if you look at this radio station, now we can clearly see it. When the gain was too low, it was impossible to see it. So we were only able to see the strongest stations. But what happens if I keep increasing the gain beyond this is that at some point I will get saturation. And I think there is something weird with the drivers I have in this machine, because it seems that there is, somewhere here is the maximum gain, and then it kind of goes back a few steps down or something. But anyhow, what I wanted to demonstrate, and probably with this small antenna indoors is not the best example, is that setting the gain all the way to the right is probably not the best option. Because if you set the gain too high, then the amplitude of the signals coming into the SDR will be very high, and you can have unintended effects such as saturation or distortion. To avoid distortion, we need to set the gain to an intermediate value. And we do not want to set it very low, because in that case, we do not receive signals. So there is kind of a sweet spot of gain that is appropriate. And the question is, how could we select the gain? And this is the recipe or trick that I want to show you here. And you can do this with any software. You will need to do that with GNU Radio to determine an appropriate gain to do with to use for your experiments. So if we set the gain to the minimum level, then we can look at the signal to noise ratio of this signal. So the signal to noise ratio is the difference between the maximum of the signal and the noise floor. This is minus 60, this is 80, so this is 20 dBs per division. So this signal looks to be about 10 dBs above the noise, approximately. If I increase the gain, everything comes up. And the reason everything comes up is because the SDR is not only amplifying the signals of interest, in this case, the FM radio stations, but also all the noise which is being received by the radio, but not its own noise. So at any time with a radio receiver, you have noise which is a combination of two sources. One is noise which is coming into the antenna, and this is physical. This is something that we would like to avoid, but it's there. It's called antenna noise or antenna temperature. And the other one is noise internally generated by the receiver. So every kind of amplifier, every kind of analog to digital converter, any kind of mixing circuit will introduce noise of its own. And what happens is the noise introduced by the device is fixed. It doesn't depend on the gain. But when we increase the gain, we increase the amplitude of the signals and of the noise coming from the antenna. So at some point, that sum of signals of interest plus noise coming from the antenna is much stronger than the noise generated by the device. And then the noise generated by the device plays a minor effect and is no longer relevant. So we want to increase the gain high enough so that that happens, but not much higher than that. For otherwise, we could have saturation, distortion, etc. And the way to do that is to increase the gain slightly, and then see if the signal to noise ratio has improved. So here we have seen that everything has come up. I will repeat. So the noise is slightly below 80. The signal is at 70. I increase this to 10 dBs, for example. The noise is now slightly above 80. By no means it has increased 10 dBs, but the signal, it looks like it has increased even more than 10 dBs, maybe 12 or 13 dBs. Why? Because these gain steps are often not very accurate. So you might be setting 10 dBs here, but actually getting 13 dBs on the hardware, or who knows. And at this point, the signal to noise ratio we have on this signal is close to 30 dBs. So it has definitely improved. If we keep increasing the gain, I'm going to try 20 now. We see that now the signal has, the noise has come up by 10 dBs. The signal has also come up by 10 dBs. And the signal to noise ratio is also 30 dBs, maybe it's 30 something, maybe it's slightly higher. But there is a point of diminishing returns when you keep increasing the gain. And at some point, you will clearly see that you no longer obtain any benefits. Okay. There we go. So I have GNU Radio Companion here. What I have done to open it, maybe I can show that, is on a terminal window. I type GNU Radio Companion. And depending on how you've installed GNU Radio, you might even have a desktop icon to run GNU Radio Companion or something in the start menu windows. I already have opened the audio demo and RTLSDR demo flow graphs. Those are in the GitHub repository, but I will be doing probably the audio demo from scratch. So what I want to do now is to click on create a new flow graph. And here I get a new tab called Untitled with my empty canvas, or almost empty canvas, because each GNU Radio flow graph needs to have these options block, which sets some top level options, and I can double click. So if I double click on the block, we get these properties windows, and it is necessary to set the ID of the flow graph to change it to something other than default. So here I'm going to say audio demo 2 to avoid any conflict with the existing audio demo. And you can set the title, author, copyright, etc., etc. Also, something which can be of interest is the generate options. So by default, the flow graphs you generate use a graphical user interface with Qt. Qt is an open source library to do graphical user interfaces. But you might have a flow graph which needs to run on a machine which doesn't have any graphical user interface. Maybe it's a server into which you have SSH access and you don't need to display any plots or anything. So you can change this to no graphical user interface, and then the run options, either prompt for exit or the most common run to completion, which will keep running until the flow graph finishes, or until you press Control-C to terminate. But for the time being, we will use this GUI option because this allows us to use the GUI blocks to display signals and also to set the values of variables while the flow graph is running. What else here? Not much of interest at this moment. Okay, so I click OK. This gets red. That means there are changes which are not saved, as it says unsaved. So what I want to do now is File Save or Control-S. And I'm going to save this as audio demo 2. And save. The other block you get by default is a variable block called sample rate or sample rate. Variables are just variables. They actually correspond to Python variables. And they can be used to hold any values that you need, also values that you obtain through complicated calculations that you want to encapsulate in a block. Here, and actually mostly everywhere in the entry fields in the GUI, we can enter any Python code we want. So I could do this plus 7 plus, I don't know, 2 to the power 8 is Python, right? So even if I think I need to click away. Yeah, if I click away and mouse over, it says the value is 224263. So it has evaluated this Python code. And this is some simple arithmetic, but I could call any complicated Python functions I want. And if I click OK, then I get this weird sample rate, which comes from this calculation. So you can use variables to hold the result of calculations. And you can change variables, and one variable might compute something, next variable might compute something based on the value of the previous variable, etc. So the reason that we get a sample rate variable by default is that almost everything we will do in GNU Radio will need to use a sample rate. We'll need to know at which sample rate the information is represented, because that's needed in all the calculations. For example, if I want to generate a sine wave which is of a frequency of 1 kilohertz, that means it does 1 cycle per second. But I need to know how many samples per second, 32,000 in this case, to know how many samples per cycle the sine wave has. So in this case, I know that I need to do a sine wave such that it has 32 samples per cycle. And that's how the signal source basically works. So yeah, sample rate, it's usual in all the flow graphs. Since we are going to use the computer sound card, we are going to use 48 kilohertz, because that's the most common sampling rate supported by sound cards. And the reason for that is basically the human hearing range. So young people can hear up 15 kilohertz, 18 kilohertz, or thereabouts. And this is real sampling. A sound card doesn't do complex sampling, it does real sampling. So you need twice the highest frequency you need to represent to comply with Nyquist theorem. So with 48 kilohertz, we can represent any frequency from 0 hertz to plus 24 kilohertz, which is half of this value. Okay. So this is the canvas. As you might have imagined, here we drag and drop blocks and connect them. This is the block list. And I think this is, yeah, by default, this is shown. But if for some reason it doesn't show on your machine, do check that you have under View, the Show Block Tree panel selected, because yeah, you can hide most of the panels on the GUI. So in here we get a hierarchy of all the blocks that we have installed, either because they come in tree with GNU Radio. So this is the core module, as it says. This is meant for blocks which are included with GNU Radio. And for every out of tree module, so for every external set of blocks that we have installed, we get another category here. So these are a few blocks to control the Allen telescope array. And these are a few blocks to control Microsoft Azure network of ground stations. So that's another example of space looking antennas that can be controlled from GNU Radio. Anyhow, we're going to use audio, and we're going to select the audio source. Source means that it is an input of samples, or it delivers samples into your flow graph. So the block has an output port here, out, and no inputs. This represents the microphone or sound card input in your computer. Since searching for blocks in the list is very cumbersome when you know their names, there is a quicker way to do that. You press somewhere on the list, you press Control F. So now I have pressed Control F, and there you get this search function, and you can click audio. And this is actually useful because you get a list of all the blocks which have audio on their name. So if you are not sure how we multiply, then you can write multiply, and you will see that, yeah, there is a multiply, but there is also multiply by a constant and multiply conjugate. So that searching might be a good way to locate what you need if you are not exactly sure in which category it is. Okay, so audio source. This is an output port. There is another option which you can change here. So this is the auto hide port labels. I think by default it comes like this. So with auto hide port labels disabled, and then you will always see the out name on the port. And for a better example here, you see out, in, out, in. So if you want to hide those, you can auto hide port labels, and then this will be smaller. This will not have any names, and you can mouse over when you want to see the name. This is useful, especially in blocks which have more ports, and some of them have larger names than input and output. Having them show up all the time wastes valuable space on the screen. So this is how I prefer, but you can adjust it to your preference. So, okay, the audio source. This is delivering samples from the sound card into the flow graph. And you can notice that this port is orange. And in some of the earliest examples I showed on the slides, the ports were blue, if you remember. So GNU Radio uses colors to represent data types. Blue means complex data, I and Q data. IQ data is usually called. Orange means real. And there's a list of types here in help types. So you get float, 60 complex float. This is the blue I was meaning. Float 32, this is the orange. And for some reason, this doesn't show in full here, but I can zoom in like this. So yeah, the most common are complex float 32, which is blue, anytime you want to represent IQ data. Float 32 when you have real values. And then you might encounter these two, so 16-bit integers and 8-bit integers, the yellow and pink, especially because we tend to do recordings using as fewer bits as possible in order to save disk space. So if 8 bits is enough, then the file might use 8-bit integers, or if not, the file might use 16-bit integers. So the block that you have to read the file might use one of the two data types, and then we will have blocks to do the conversion to either this orange or this blue, because working with floating point data types on the computer is much easier than working with integers. Probably you already know that if you've done any sort of math, you need floating points to represent the values that show up.
Hey, Daniel.
Yep.
There's a little bit that's blocked at the top of the screen. I guess there's another window that's not getting shared. So we see sort of most of your screen, but there's a little rectangle at the top.
Yeah, I think it's like the Zoom share screen thingy, which for some reason in Linux stays at the top and never disappears. But as long as you're able to see do you see the file menu?
Yeah. We do. It was just the top of that menu that you're pointing at. We didn't see, but I think it's generally fine. We see the majority of your screen. So.
Yeah. Okay. So generally, you see indeed the full window of the application with that other screen with the data types. You might have missed that on the very top there was a blue for complex data type, but that's all there is to it. Thank you, Steve. Okay, so what do we do with this audio source? Maybe we want to represent the signal graphically. And for that, we have, I think it's called instrumentation. Yeah, I always search for this by name, so I don't know in which category they are. So instrumentation means looking at signals. This comes from electronics. You have an instrument and you plug it on your circuit to look at what is happening. So Qt is the most common one to be used, and we have a bunch of those. We are going to use the time sync for the moment. Time syncs means a time domain representation. So it will represent signal amplitude versus time. If you've ever used an oscilloscope, this is like a virtual oscilloscope. So we get this Qt GUI time sync. And the data type for the input is blue. So that means it's expecting complex data. This doesn't match the audio source. And in fact, I'm going to connect them to show what happens when you have non-matching data types. There are two ways to connect blocks. The first is you click on one end and you click on the second end. So with my second click, this line appears and it's red because the data types are mismatched. And there is these flow graph errors here. So if we click on view flow graph errors, we get some helpful information. So source IO type float does not match sync IO type complex. And this is for a connection between audio source 0 and Qt GUI time sync x0. So pretty self-explanatory. And also the size doesn't match because a float is 4 bytes and the complex data type is 8 bytes, not surprisingly because it's a pair of floats. Okay, so that's great. The second way to do connections is you drag and drop. So you drag and drop. And again, we get the same. We can let this connection stay and instead change the data type. So we double click and on the properties, we select float as type. And we can either click apply. So apply applies and doesn't close the menu. And you can also click OK. OK applies and closes. So now we have a perfectly valid flow graph. These view flow graph errors cannot be clicked because there are no flow graph errors. And now we get these two buttons. One is generate the flow graph. So here it says generating blah, 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 audio demo 2.py. It has generated a Python script which represents the flow graph. And if you wanted, you could run these from the terminal. You could do Python audio demo 2.py or even /audio demo 2.py to run the Python script. But a quick way to do that is press this execute the flow graph button. So when we press execute the flow graph button, what we see is basically the waveform of my voice as I'm speaking on the microphone. You can see that when I stop, there's nothing, just background noise. And when I'm speaking, we can see how my voice looks like as if I had plugged a microphone into an oscilloscope. And oftentimes when signals come from hardware, they are normalized to be of maximum amplitude 1. That means the range of values you can represent is from +1 to -1. And here I'm not speaking as loud as the microphone can capture. So I'm barely getting 0.5 amplitude. Anyhow, there are many more options we can change. We can in fact change some of the options live. So if you have a middle mouse button on your computer, and that might be a tricky thing on Mac, but it works on Linux and PC, you can middle click and maybe press stop. and then the flow graph stops. So I continue speaking and nothing happens. This is a good way to freeze whatever is being shown in case it's of interest and you want to do measurements, because as you might have realized, I have a mouse cursor here and it's showing me time and amplitude wherever I point. We can resume, and we can also change some of the line properties, color, red, etc., etc. We can display points, so for example, line marker, circle, and that displays points as circles. That's more useful if we want to zoom in, so let me demonstrate that. If we want to zoom in, we can drag and drop, and then you select the area you want to look at, and with the right mouse button you go back to the previous zoom level. So this is the basic controls of the time sync, and the frequency sync, which we will also use now, works similarly. So what can you do if you don't have a middle mouse button? That also happens often. There is, I think, in config something which is called the control panel. So you can select control panel yes under config. And as you can see, you can edit most of the options we had available before. And then when you press play, there are at least a few options you can change here, such as auto scale, which changes the vertical scale to match whatever is happening. So even here we can see the noise. And then I know the scale is very wide, so we need to zoom out, and we can do that with the scroll wheel of the mouse, or either with some of these controls. So the wide range, I presume, yeah. So this is the properties or control, or however it's called. Something else which is very useful, and most of the blogs have this, is if you go to properties, there is some documentation tab, and then there is a link which says visit wiki page. So there is a GNU Radio wiki, which has documentation for most of the blogs, and in the documentation you can see an explanation for each of the parameters of the blog, and oftentimes you can see an example trying to show how to use that blog in practice. And maybe in special cases you get some additional demonstrations, such as here how to use the trigger, and also the links to the source code files in case you want to see how this is implemented. And probably this is a fairly complicated block because it's doing it's drawing on the computer screen. But if you have simple signal processing blocks such as multiplication, maybe you want to see exactly how multiplication is done or whatever. So, okay, what else is useful here? If you go to the main page of the wiki, there are some tutorials. So this is a great collection of tutorials. There are some beginner tutorials. There are some intermediate or advanced tutorials, which tell you how to do some complicated communication algorithms such as OFDM. So this is really helpful. We will probably look at a few of these at some point, but not today. Anyhow, second type of very useful display block is the frequency sync. The frequency sync is used to represent signals in the frequency domain. So it does a Fourier transform and represents the output for you. So instead of seeing amplitude versus frequency, amplitude versus time, such as in the GUI time sync, you will be able to see power or amplitude versus frequency. If this is like an oscilloscope, this is like a spectrum analyzer. So again, we change the data type to float, and something that I like to change is the FFT size, so that's how many points are represented on the screen, how much frequency resolution you get. The default of 1024 seems a bit low to me. I prefer 4096. So I always set it like this, and then we can do a connection. So now what I see here is the frequency. And there is something very interesting about this headset that I'm using. It's a wireless headset. And it wasn't obvious in the time domain display. So what you can see here is that, yes, the computer sound card, or actually the virtual sound card USB thingy used by the wireless headset, is doing 48,000 samples per second. So it's able to represent that up to 24 kilohertz. But if you look at here, there is really nothing. There is a low pass filter here at about 7 kilohertz. So only between 0 and 7 kilohertz of my voice are being recorded by this microphone. This is just because of the electronics of how the microphone is built. And you can do the same kind of experiment. If you have a microphone or any other kind of thing, you can plug into your computer audio input. And you can also, I don't know, listen to some signals that do not change so much to try to see what is their frequency content. To make that easier, some options which are useful here are the maximum hold and the minimum hold. If you're familiar with the oscilloscope, those are the same. So the maximum hold and the minimum hold, what they do is basically to hold the maximum value. So you see in blue, it's updating as I'm speaking, but in here, this, I don't know, yellowish color is the maximum power that at some point in time my voice achieved. And this is the minimum power. So this is useful if signals appear and disappear.
Can you explain why we're seeing negative frequencies in the
Oh,
default?
yeah, that's a great question. Yeah, so when we have a real signal, there is no such thing as a positive frequency and a negative frequency. Or another way of saying that is that the spectrum of a real signal is symmetric about 0. So there is the same frequency content on positive frequencies and negative frequencies. In fact, if you think in physical terms, I'm now speaking, my voice is producing some frequencies, I don't know, 3 kilohertz. What does it mean to say minus 3 kilohertz in this context? It doesn't really mean anything. It doesn't have a physical support to it. So what happens is if you plug this real signal into the Fourier transform, you get a symmetric spectrum. The Fourier transform always by default gives you negative and positive frequencies. So now that you know that, what you can do if you do not want to see those negative frequencies, just because this is a mirror image, and you can look very attentively and see that it is actually a mirror image. So what you can do when you have the floating point selected, the floating type selected, is spectrum width full. This is what we had. This means both negative and positive frequencies, and spectrum width half, which means display just the positive frequencies, and you get something which might be physically more meaningful, or I don't know. But the important point is this is something that holds true for real signals. For complex signals, which is the ones that are most commonly used in radio frequency processing, we do have negative frequencies as well as positive frequencies. That's the main thing that complex numbers allow us to have. And those are not symmetric, so you have different contents on the negative part of the spectrum and on the positive part of the spectrum. And the physical meaning of those negative frequencies is very clear. The meaning is that I'm tuning my SDR to some frequency. We will do a flow graph with the SDR and we will tune somewhere in the FM band. For example, 90 megahertz. So when I see a positive frequency, maybe plus 10 kilohertz, such as here, it means 90 megahertz plus 10 kilohertz. When I see a negative frequency, minus 10 kilohertz, that means 90 megahertz minus 10 kilohertz. So the 0 that I see here is not actually 0, but rather the center frequency I'm tuning on my SDR. And using complex numbers is what allows us to represent a bandwidth around the center frequency rather than having it start at some value and going up.
Thanks.
Any other questions about this? Okay, so the next thing is the mirror part to this in a certain sense, which is to use the speaker or the sound card to generate some audio that you can listen to. And I don't know if I have, if I am sharing audio on Zoom, I don't care. It's a bit annoying because I will be generating sine waves, and those are not the most pleasant thing to listen to, especially if they're loud. But it's a good thing you can do to experiment with something else that I want to demonstrate, which is how to have some variables on the GUI so that you can change some parameters in real time and interact with the configuration of your flow graph. So what I'm going to do is to drop here a signal source. And by default, this is using the sample rate. So having a sample rate variable is very helpful because by default, every block that needs a sample rate will come configured to use sample rate. And then I need floating point. I want a cosine. And what I'm going to do is to type here frequency. This will be the name of a variable that we will create. So now this is in red. It's complaining that value frequency cannot be evaluated because name frequency is not defined. Yeah, we haven't done so yet. And the same for amplitude. So amplitude. And now I have these two names. I haven't created the variables. I will do so now. I can create variables like this, but these variables have fixed values. What I want to do is to use the GUI widgets. So widgets are fields that you can interact with in your application, such as buttons or text entries. The one we will use is the entry. This is a text field where you can type in 1000, press enter, and there you go. You have updated the value to 1000 Hertz. So for the ID, I need to choose a matching name with respect to what I used here. This is going to be the amplitude. I'm going to set it at 0 by default because I don't want to have anything which is deafening me. And next, I also want a GUI entry. So what I'm going to demonstrate is how to copy and paste blocks. We can copy and then paste or Control-C, Control-V with anything which is selected. And you can even select a whole bunch of blocks and connections. You can Control-C, Control-V. And yeah, that wasn't smart because if you select blocks and connections, you need to select both the source and the destination. So with all of these selected, Control-C, Control-V will do the obvious. I now have two of these, and that's a good way to build up larger flow graphs. So frequency, this is the frequency in Hertz because this is the frequency in Hertz. And if you look at the documentation on the wiki, it will say it is in Hertz. And what else? Let's do a couple blocks like this. Not two time sinks, but rather time sync and frequency sync, so that I can see the waveform I'm generating and also audio sync. So the audio sync is the sound card output. This will come out of the speakers or headphones or anything you have connected. Do I have everything correctly set? Yeah, I think so. So let's play, and yeah, I get a scroll wheel here because, or scroll bar here because I have too many plots. So maybe what I can do is to disable the first two. That will also lead me to how to disable blocks. So there is a very useful feature, which is disabling a block, and you can left click and click disable. or you can select and click D on the keyboard. So the letter D, as it says disable D. And then the block becomes grayed out. If it disappears suddenly, make sure you don't have, or you have hide disabled blocks. This is very confusing to have it enabled because you have parts of the flow graph that you don't know that are present, and you're wondering where did my flow graph went. So I'm going to disable these to make it easier to see. And now we have these two. So currently we do not see anything because the amplitude is set to 0. So I'm going to set it to a very small number. And I can already listen to the sine tone on my headphones. I'm not sure if it's sharing over Zoom or not. I don't really care. As I said, it's a bit annoying. But anyhow, you can see here the 1 kilohertz tone and the fact that the amplitude is 0.01. So I'm going to turn that off. And yeah, basically these work as you would expect. You can change the value here. You can press enter, and then you can update the value. So now I have set it to a very small number, and we can do 2 kilohertz, and it will move to 2 kilohertz. We can even do scientific notation. So 2E3 means 2 kilohertz. This means 500 hertz, or you see how this works. So, okay, this already gives you a good notion of how to make simple flow graphs in GNU Radio and connect them, experiment with them, and control a few values. Things you might want to experiment using this flow graph as a basis is what happens if we change the waveform. Is there any difference between sine and cosine? How is a square wave or triangle or sawtooth wave any different? Does it affect its frequency content? How does it sound? So you can play changing those. And also you might be interested in looping back this signal you play on the speakers through to the microphone and doing some kind of measurement. That is often done in radio frequency when you want to examine how some radio frequency circuit behaves. You have a signal generator which is inserting or injecting some signals in the circuit. Then the signals move through the circuit. Maybe it's a filter. And at the other end, you measure those signals. And if it's a filter, you see how the frequency content has changed. So you can do some sort of similar experiment using your microphone or your sound card. And you can also generate ultrasound with this, as long as your speakers are able to do that ultrasound frequency. So by changing the frequency, you might be able to realize that you are able to listen to 12 kilohertz, but not 13, or who knows. Okay, next up is the RTL-SDR demo. So I'm going to do the same RTL-SDR demo 2. Save here. And what I'm going to do here is to show how to use the RTL-SDR in GNU Radio. So the same thing we did in gqrx before. What is the equivalent here? So yeah, first thing first, sample rate. We are going to use the same as before. 2.4 million samples per second. You can type the number completely, or you can do 2.4 E6, which is faster. And GNU Radio always displays numbers with these international system prefixes, so 2.4 million, 2.4 K, or whatever. If I search here for RTL, You might have the same SI or you might have different. It depends on whether you have SOAP installed or Osmo SDR installed. These are driver stacks for SDRs, and both of them can be used with the RTLSDR, and each of them has their own advantages and peculiarities. So I'm going to drag and drop the two of them and demonstrate their main differences. So as you can see, the sample rate is already set. This one is probably a bit more complicated than this one to set up, because as you can see here, it has more configuration parameters, and some of them do not even make sense for these SDR. So number of motherboards, number of channels, that's one. This SDR doesn't have different motherboards or channels. So, and also sync. Those are generic options which can be used for other SDRs which support them. But the frequency we can set. So we can go 98.8, which is the same FM station we tuned to before in gqrx. And what else? Yeah, RF gain, IF gain, BB gain. RF means radio frequency gain, IF means intermediate frequency gain, and BB means baseband gain. So as the signal comes in from the SDR, it might go through, and I'm saying it might go through, different amplifiers at the radio frequency level, at the intermediate frequency when those radio frequencies have been moved to a lower frequency, and finally at the baseband frequency level when things are at low frequency, around 0 hertz. And I said it might because this is kind of an abstract model about what a generic SDR might have. And in the case of different SDRs, this might map to the settings that the SDR actually supports in different ways. So what I'm going to do, because I never know how this works, and you don't know either, is to set variables to control each of them, and we will experiment and see which of them do any effect and which of them do not do any effect. So that means they are not available as an option on the RTLSDR, and so their values are ignored. So antenna we leave blank. There is only one antenna, no need to select anything. Bandwidth 0 as before. And I think there is nothing of interest in the advanced tab for now, but other times you have like RF options or something similar. So, okay, I'm missing RF gain, IF gain, and BB gain, which I will add next. What else? I'm going to set the options of this one to compare. So device arguments, let's leave blank. The other one also did have device arguments. This is to select what device you have. So if you have multiple RTLSDRs plugged to the same computer, for example, each of them will have a different serial number, so you can select the one you want by serial number. For example, that's one thing you can do with device arguments. In this tab, there is not much else than sample rate. So there is also RF options. And RF options is where the frequency lives. So by default, there's a variable called frec that we do not have. I'm going to do 98.8 megahertz. AGC, that's a good point. I've sort of ignored AGC for now, but let's say a couple of sentences about AGC. AGC means automatic gain control. That's basically a hardware feature on the RTLSDR, which adjusts the gain automatically according to the signal levels that it is receiving. In principle, that would be great if it worked great, but it doesn't work very well. In some scenarios, it works well. In some, it doesn't. So it's probably it's probably better to set the gain manually, especially in those cases where you are experimenting in real time with the SDR. You can imagine that if we build a receiver which is going to be fully automated, then there is not going to be anyone around to adjust gains. So then using AGC is mandatory. But if you are driving things manually, such as here, then for me, it makes more sense to adjust the gain manually. So we leave this to false and we set RF gain. Here, there is a single control for the gain. Okay, so let's add variables. Not variables, sorry, but entries. Something important about the entries, they also have a type, and by default is integer. I already changed that to float before, but I didn't say it, so I'm making it clear now. RF gain, it's a float, and by default, 0. Usually decibels. These come with decibel values. IF gain, I'm basically copy and pasting so that I only have to change the ID here. And now this one is happy, 0, 0, 0. What else do we need? A frequency sync. Where is it here? So connect and FFT size 4096. I need to have one of these two enabled and one of these two disabled because I only have one RTLSDR stick. So if I try to use both of them at the same time, both of these two blocks, the two will fight for ownership of the RTLSDR. We do not want that to happen. So first I'm testing the RTLSDR source. I keep play, still I have my RTLSDR connected from before, and we see this FM station the same as before, moving in the spectrum. And the gain is also very low. And we can also notice that the amplitude levels do not match the ones we saw in gqrx. This is because amplitude here is fairly arbitrary. It also depends on the FFT size you use and on how you normalize your FFT. So if you're using these values for anything other than relative measurements with exactly the same tool or settings, you need to account for all of that. So I basically do the same and increase RF gain. And yeah, this increases the signal by some amount, 20 dBs. It increases the signal, 30 dBs, more signal. Okay, I also want to try this. And these do not do anything. I can even set 100 and it doesn't do anything. And it's not just because this is high. So if I set things back to 0 and then I type in here 100 or 1 million, or I might type whatever I want, this field is being ignored by the driver because the RTLSDR doesn't have this IF gain. And the same happens with BB gain. So if you encounter any other kind of SDR you need to use, you know how to experiment and see how the gain controls are mapped. So yeah, 25 maybe for this kind of antenna, this kind of environment is a good gain, or anything between 20 and 30. Something else which might be appropriate to show here, because these are FM stations and they modulate voice or music. This is a classical music station, so depending on the kind of music that is being played, the spectrum will change and jump around. So maybe that's not so useful for measurements. What we can do is an FFT average. That is again middle mouse click to get this menu, or it can be changed in the properties. And we can do medium averaging. So averaging or surprising, even though the signal is changing its shape on the spectrum, we get something which is more steady by averaging. Okay, what else? Second, RTLSDR source. I connected. I can even leave the two connections because this connection is disabled since this block is disabled. And the same thing, now I know that the IF gain and BB gain do not do anything because the block here doesn't even have those options. The only option that the block has is RF gain. So let's check that the RF gain works as expected. Yeah, 10, 20, 30, and it's the same as before. And I'm doing these kind of checks quite thoroughly because oftentimes setting up SDR configuration can be a bit confusing if the drivers have some bugs or some quirks. So this is a good way to do it. Okay, what else? There is not so much more I want to say for this session other than feel free to test your RTL-SDRs in GNU Radio, in gqrx, or in any other application you find. Reach out to me if something doesn't work as expected. Even if you had GNU Radio installed correctly on your computer, maybe you need to do some extra steps to get the RTLSDR running, or maybe you have some driver problems. Regarding that, here there is something which can be helpful. This is Radio Conda. I'm going to paste this in case it's helpful. So this is Radio Conda. And RTLSDR, where is it set up? And in Windows, you need to do something which is to install some driver using an application called Zadig. In Linux, you might need to do this thing for blacklisting the digital television modules, because probably that's interesting. The origin of this device, this is actually a digital television receiver. People wanted to have some hardware to receive digital television in their computer, specifically the kind of digital television protocol that is used in Europe, which is called DVB-T, not the one which is used in the US. So there is this very inexpensive hardware. And then someone noticed that there were some undocumented options in the hardware that could be used to stream IQ data on the computer. And instead of using that to receive digital television, to be able to use it to receive anything that might come to mind, FM radio, all sorts of radio communications, GPS, etc., etc. And the reason for that, this wasn't a coincidence by any means, is that when they made this hardware product, they not only thought about selling it for digital television, but also for FM radio. And the most simple way of doing FM radio was not to do it on the hardware, because that would have increased the cost, because you need to have a chip in there to do FM radio, but rather to do it in software. FM radio processing is simple enough that any computer, even 10 years ago when this device came out, could be used to receive FM radio. And that's the reason that this device had this capability to stream IQ data on the computer. But it wasn't really known until some open source developer stumbled upon this capability and realized that it was a wonderful feature, and that people might want to use that for many more applications than FM radio. And I think by now they have sold more and more chips to be used as an SDR than to be used as a digital television receiver. So anyhow, these are instructions for Linux users. I don't know what happens with macOS. So if anyone is trying to use this in macOS and it doesn't work out of the box, let me know. I can reach out to some people using macOS and we will find out what needs to be done. Okay, what else? Yeah, finally, feel free to explore the radio frequency spectrum. This device is great because it allows you to tune to anything between, it depends on the particular device you got, but maybe between 20 something megahertz and 1 point something gigahertz. And there is a lot of different stuff out there, and you can search online where different services are located in. In fact, here on my back, there is a poster about different communication protocols and the bands they use. It shows the different cellular telephone bands, and some of them you can receive with the RTLSDR. So around 700 megahertz or 800 megahertz or 900 megahertz, you might be able to see some cell phone signals. And if you have your cell phone at hand and either place a call or have data services and start playing some YouTube video or doing some traffic, you might be able to see very loud signals pop up on your SDR. And yeah, that's your cell phone transmitting. So it might be interesting to search where your cell phone is transmitting. That will depend on which cell it has associated with. And as I said, these signals will be very, very loud because, yeah, your cell phone is transmitting 100 milliwatts or something on that order, and it's maybe a couple meters away or a few feet away from your SDR. So the signal arriving on the SDR is huge. So huge that even if you're tuned to another frequency, you might be able to see some effects because of distortion or intermodulation. So that's also another good demonstration that these devices are not ideal devices. They are real world electronic devices, and they have their own limitations and their own problems, such as if there is a very strong signal, then it's difficult to receive everything else, and the strong signal tends to pop up everywhere in the spectrum, even if we intend to receive a different frequency. So that's all for today, unless there are any questions or comments.
Thanks very much, Daniel. Anyone have questions? Anyone online? Okay, well, that was sorry, Daniel. Yeah, great introduction. And we'll post this video online as well if folks want to review it. But Daniel is, as I said, very generous, both in terms of giving these lectures, but also with his time and helping folks troubleshoot. So do reach out if you have any issues.
Thank you. Great. See you everyone next week.
Thanks, Daniel.